Today we continue our study on small signal stability of a single machine infinite bus system. Now, today we will include the effect of synchronous machine field circuit dynamics in the small perturbation model. Earlier the transfer function model which we developed earlier, in this transfer function model we assumed the constant field flux mode, okay, or the voltage behind direct axis tangent reactance was assumed to be constant, that is the classical model. Now, we go one step further and include the dynamics of the synchronous machine field circuits. Okay. Now, when we developed the synchronous machine model, okay, at that time I emphasized actually that if we neglect the amortisseurs, then the synchronous generator can be represented by a first order model. That is, the synchronous machine equations, there was only one differential equation. The differential equation was corresponding to the field flux linkages, and the equation when it is written considering time in seconds is put as P psi f d equal to omega naught into E f d minus R f d I f d. Now, this term omega naught comes because we are now considering the time in seconds rather than in per unit. Okay. Because when we develop this equation in per unit, it was simply d by dt of psi f d equal to E f d minus R f d I f d. Okay. Now, here we will do once that transformation, because this equation is written considering this E f d and I f d in reciprocal per unit system. Okay. We replace this E f d by this term using this equation E f d equal to L a d by R f d E f d. That is, when we derive the synchronous machine model, we introduce this term E f d, and basically this introduction was to link the non reciprocal per unit system to reciprocal per unit system. And here when I replace this E f d by the field flux field voltage, that is E f d is the field voltage or output of the exciter, right. The equation becomes P psi f d equal to omega naught R f d divided by L a d u E f d minus omega naught R f d I f d, right. Therefore, this is the additional equation that has to be considered while accounting for the field flux dynamics, or we can say the field circuit dynamics. The complete model considering the rotor dynamics and the field flux dynamics can be written in this form, that is these first two equations represent the dynamics of the synchronous machine rotor. Okay. These two equations are well known to us. Now, to these two equations, when I add this third equation, that is d by dt of psi f d equal to omega naught R f d L a d u into E f d minus omega naught R f d I f d. Okay. Now, these three equations right describe the complete behavior of the synchronous machine under dynamic conditions, including the field flux dynamics. While writing these equations, we have made one assumption, and that assumption is that the amortisseurs are ignored. Another assumption which we have made is that the transformer voltage terms are also neglected, and the speed deviation, that is the omega r term which appears in the stator equations, stator voltage equations, that omega r is also assumed to be equal to 1. Okay. Now, when we look at these equations, we can clearly see that the state variables are delta omega r, delta and psi f d, that is these are the 3 state variables. Okay. But when you see on the right hand side of these equations, we have a term T, that is the air gap torque, right. Now, this air gap torque is neither a state variable nor it is a input to the system. Similarly, this IFD, that is the field current, is not a state variable or nor it is a input to the system, because when we write the equation, this Tm is the input to the system, okay. EFD is the input to the system, that is the mechanical torque applied to the system and the field voltage applied. Therefore, they are the 2 input quantities, and these are the 3 state variables, while this TE and IFD, these are not the state variables as well as they are not the input quantities, and therefore, there is a necessity to express these 2 quantities TE and IFD in terms of state variables. Okay. The moment we succeed in expressing the air gap torque and the field current in terms of state variables, we can write down the complete model of the system, because these equations are concerned. In these equations, right, we have these quantities which are to be expressed in terms of state variables. Now, to express these quantities in terms of state variables, we make use of the synchronous machine equations, and we will also make use of the network equations, because here we are considering a machine connected to infinite bus, right, and therefore, the transmission line, right, represent the network. Therefore, we will be in a position to write down the network equation, we will be in a position to write down the synchronous machine equations, and since these 2 components are connected, right, we will be in a position to correlate them. Okay. That is, we will find actually the network constraint equation. Okay. Now, these are the 3 basic equations which represent the d axis field flux linkage, q axis field flux linkage, and the field winding flux linkage psi f d. Okay. Psi f d is a state variable, while this psi d and psi q are not the state variable, but we can see here that psi d can be expressed in terms of these inductances ID that is the direct axis component of the synchronous machine stator current, and IFD. Now, these equations are known to you. Further, actually this ILFFD, this is the self inductance of field winding. This will be expressed as LAD plus LFD. LAD is the mutual inductance, and in the reciprocal per unit system, right, these mutual inductances are same for direct axis stator winding, the field winding, okay, these are same. We have made these equations same. Then we will make use of this equation, that is the air gap torque is equal to psi d IQ minus psi q ID. Okay. Therefore, with this we will be in a position to simplify the model. Now, these steps are clearly given in the textbook which is prescribed for your course. Okay. To start with, what we did, write that this psi d, this is the direct axis flux linkage, can be expressed as minus LL ID plus LA DS into minus ID plus IFD. That is, if we make use of this equation, right, then what we do here is that this LED these two terms are combined, and further we will make use of this the saturated value of the mutual inductance. Instead of using the unsaturated value, we will be using the saturated value, and the saturated value and unsaturated value are related by the saturation coefficient. Okay. And therefore, the equations now which I am writing here for psi d and psi q, this LED is replaced by LEDS, that is we are using the saturated value. Okay. Therefore, this term, we can see this term, that is LADS into minus ID plus IFD, this term represents the flux linkage, this flux inductance into current, and this we will denote as psi AD. Psi AD. Similarly, for psi q, we will represent this as minus LL into IQ plus psi AQ. Now, here we are using these terms which are normally called the intermediate variables, which will ultimately be eliminated. Okay. Similarly, this equation, that is the field flux linkage equation psi FD, right. Now, for this LFFD, you substitute LAD plus LFD, okay, and then these LAD terms will be combined. The terms which have the coefficient LAD you combine, and we can write the equation for field flux linkage in this form psi AD plus LFD IFD, right. Now, when we write this field flux linkage in terms of psi AD, which is also appearing in our other two equations, that is psi D equal to minus LL ID plus psi AD. Okay. Therefore, the first step here is that now I express this IFD, that is the field current, in terms of psi FD, which is my state variable, psi AD and LFD. LFD is a parameter of the machine, is a machine parameter, okay, synchronous machine parameter, this is known quantity. Therefore, this is one step where we are now expressing the field current in terms of the one of the state variables and psi AD and LFD. That is, this term is additional term which again we have to eliminate. Now, these steps you can perform yourself, that is the psi AD was defined as minus LADS IAD plus LADS IFD. That is, this term when we put in the expanded form, right, it was minus LADS into ID plus LADS into IFD. That is, it was written as LADS into minus ID plus IFD. Okay. This can be simplified and now expressed in terms of ID, that is the direct axis current ID. This derivation one can perform and obtain the expression for psi AD in terms of direct axis current ID, direct axis component of the synchronous machine current ID and psi FD. Therefore, if you see this equation, that this psi AD has been expressed in terms of the terminal current, a component of the terminal current, and the psi FD, which is the state variable. Okay. Similarly, you can express psi AQ in terms of IQ. That is, what we are doing here is that these two terms, which are the intermediate variables psi AD and psi AQ, have now been expressed in terms of the state variables and the direct axis and quadrature axis component of stator current. Okay. Now, these two steps are These steps are very important. Then we will be further making use of the stator circuit equations now, because the stator circuit is connected to the infinite bus through a transmission line, that is a machine infinite bus system, right. And we have the standard equation, that is the E D equal to minus psi q into R A I D, E q equal to psi d minus R A I q. These are the stator circuit equations. These are the algebraic equations, the stator circuit equations, okay, where this psi d and psi q can be written in terms of currents, that is I q and there is little mistake here, I d. Okay. Now, in these equations we see here very interesting thing, that psi q and psi d are expressed in terms of our intermediate variables psi a d and psi a q and I q and I d. Okay. Now, what we do is we write down the network equations, okay, and then once we write down the network equation, we will be in a position to write, we will be in a position to eliminate this E D and E Q. Okay. Now, to do this thing, we write down the equation for E D and E Q, which were earlier written in this form, that is this psi q and psi d terms will be replaced by these terms. Okay. So, that E D and E Q are written in terms of psi a d and psi a q. Okay. Therefore, the direct axis and quadratic axis component of the stator voltage is now written in terms of the currents and these intermediate variables. Okay. R A, L L, these are the circuit or the synchronous machine constants. Now, let us see what are the network constraint equations. Okay. Now, to understand this network constraint equations, what we have to do is we make use of our reference axis, right, because in the machine infinite bus system, right, the infinite bus voltage can be represented as a reference and the rotor position can be described in terms of position of the q axis, right. The position of the rotor with respect to the infinite bus voltage phasor can be expressed in terms of q axis. That is, here if I represent this as my infinite bus voltage, okay, and this is the terminal voltage of the machine, synchronous machine, right. If this is my q axis, this is E D, that is the d axis, that is this is your q axis, okay. This is all known to you, okay, and this is your d axis. Okay. Then the definition of this power angle delta is the angle by which q axis leads E B. The delta is positive when q axis leads the infinite bus voltage by an angle delta, while the internal angle is the angle by which q axis leads terminal voltage. The delta I is the internal angle and delta is the power angle, total power angle. Okay. Now, here you can write down the components of infinite bus voltage, that is, if you resolve this infinite bus voltage E B into two components, one along q axis, another along d axis, then the component along q axis is E B q, which is going to be E B cos delta. Component along d axis will be E B d equal to E B sin delta. Okay. And when you express this terminal voltage and infinite bus voltage as phasors, we can write down terminal voltage as E d plus j times E q and infinite bus voltage as E b d plus j times E b q. Okay? This is very straightforward, nothing to be explained. Now, let us write down the network constraint equation. This is your synchronous machine. Terminal voltage is E t, phasor. The line impedance is R e plus j times x e, and here is our infinite bus. The phase, the voltage here is E b phasor, right? And I t, the current here, is written in the phasor formula, right? Therefore, our network constraint equation is E t is equal to E b plus R e plus j times x e into I t. This is the network constraint equation, a very simple equation which relates the terminal voltage of the synchronous generator to the infinite bus voltage in terms of the line impedance and current. Okay. Now, what we will do here is that we will replace now E t by E d plus j times E q, E b will be replaced by E b d plus j times E b q, I t will be replaced by I d plus j times I q, and then we will equate real part with the real part and imaginary part with the imaginary part to get two algebraic equations, okay, in terms of the real variables. Now, this exercise has been done here. This is our network constraint equation. Okay, I am just reproducing here. You substitute in this equation, replace this E t, I t and E b by the components, and you perform simple algebraic simplifications, and you will get these two equations, that is E d as E d equal to E b d plus I d into R e minus I q into x e, E q equal to E b q plus I d into x e plus I q into R e. Okay. This is very there is nothing very difficult. Okay, anybody can do it. Now, once we have done this, we can now express this current I d and I q in terms of our state variables. That is, you make use of this is one, they are the two equations where E d and E q are expressed in terms of these are our intermediate variables I d and I q. Okay. Now, this E d and E q will be replaced by this E d and E q, right. You replace this by the expressions given on the right hand side of these equations, right. Therefore, once you do this thing, you will get equation, right, where you have only I d and I q, and they will be written in terms of these terms the intermediate variables psi aq, psi ad and other machine parameters. And ultimately, when you do all the simplifications, algebraic simplifications, you can write down the expression for ID in terms of the state variable. This is your state variable, this is also a state variable, and other synchronous machine constants. That is all the previous steps which we have made are basically to come to a stage where we can replace, we can obtain the expression for the ID and IQ in terms of these state variables. Okay. Similarly, the expression for IQ is given like this, which you can derive yourself. You have to sit and derive these equations. The definition of the terms which appear in those equations are also expressed here. Okay. And further, when you write these terms in our per unit system, the line inductance or synchronous machine inductances are equal to the synchronous machine reactances and line reactance. Okay. Therefore, we do not make any difference between the inductance and reactance, because in per unit system our omega O is 1. Okay. Once we have obtained the expression for ID and IQ in terms of the state variables, okay, the model is complete. It comes out to be non-linear model. If you look it very carefully, then you find actually that the psi AD and psi AQ terms are expressed in terms of these currents. Okay. And these currents are now expressed in terms of state variables. We have also seen actually that the air gap torque is expressed in terms of the flux linkages and currents, right. Therefore, ultimately what happens is that we are in a position to express the torque term which comes actually in the equation for the synchronous machine, that is the swing equation, in terms of the state variables. Torque is expressed in terms of the state variables, right. Now, these are the non-linear equations, we have not done any linearization. Now, this we can obtain now the linear equations considering small perturbations. The first step which is considered for linearization is to obtain expression for incremental changes in ID and IQ, to obtain the expression for incremental changes in ID and IQ. This ID, which is function of these state variables, okay, you can obtain the expression for incremental changes in terms of the state variables. That is, delta ID can be written as m1 times delta delta plus m2 times delta psi ft. These m1 and m2, right, these are the quantities which depend upon the synchronous machine parameters, the line parameters, the initial operating angle of the system, that is delta O, that is the operating condition of system. That is these two equations which are the incremental equations for currents, direct axis current and quadratic axis current, are now written in terms of the state variables, and these coefficients are function of system operating condition and system parameters, which includes the synchronous machine parameters and the line parameters. Okay. Now, here actually I have derived the expressions for M1, N1, M2, N2, and it can be clearly seen that these constraints are function of the machine parameters and initial operating condition, that is delta naught here, sin delta O, where you find cos delta O term, all these line reactances, the infinite bus voltage. Okay. Now, to complete our model, we also obtain now the incremental changes in these intermediate state variables, that is delta psi a d and delta psi a q, in terms of our state variables. For example, delta psi a d can be written in terms of the incremental changes in the state variables, that is delta psi f d and delta delta. Delta psi a q can be written in terms of, again in terms of these state variables, and the coefficients of these terms are again function of the machine parameters, system parameters and operating condition. We had written the expression for IFD. If you just say this equation, see the equation here, this equation, IFD was expressed as psi FD minus psi AD LFD. Okay. Now, since psi AD is expressed in terms of the state variables, I can now express incremental change in the field current in terms of the state variables. The expression comes out to be as delta IFD is equal to this coefficient into delta psi FD and this term into delta delta. That is, incremental change in field current is expressed in terms of the state variables. Incremental changes in the intermediate variables, that is psi AD and psi AQ, are expressed in terms of the variable, because psi AD and psi AQ have to be ultimately eliminated. Now, we come to our main equation, that is the expression for air gap torque. We have to write down the incremental change in air gap torque, that is delta TE. Delta TE, as we have seen earlier, delta T is written as, I am saying not this, first we write down delta T, not delta T. T is written as psi d I q minus psi q I d. Okay. Now, this psi d, right, if you consider the leakage inductance, then to obtain the expression for air gap torque, this psi d has to be replaced by psi a d s I q minus psi a q s I d. We will be considering the saturated value of these flux linkages, right, and difference between this and this term is the leakage flux, which is not contributing towards the air gap torque. Okay. Now, we want to linearize this equation. To linearize this equation, the simplest way will be, you write down this T E as T E O plus delta T E express this term as psi A D S O plus delta psi A D S IQ will be expressed as IQ O plus delta IQ minus, this is also perturbed, psi A Q S O plus delta psi A Q, right, into I D is expressed as I D O, I D naught plus delta I D. Now, under steady state condition, T E O is equal to psi A D S O I Q O minus psi A Q O S O into I D O. Okay. And we will neglect the terms which are the product of two incremental terms, like when I multiply these expressions or simplify, I will come across the term incremental change in the psi AD multiplied with incremental change in current. These two incremental changes, when they are multiplied, will give you very small quantity which can be neglected. Now, when you do this exercise, ultimately you can write down delta T E equal to psi A D O delta I Q plus psi I Q O delta psi A D minus psi A Q O delta I D minus I D O delta psi A Q. Here actually we are considering the saturated values, S is not written just for the simplification. Okay. Now, we have the expressions for delta I D and delta I Q. We have also obtained the expression for incremental changes in the air gap flux linkages psi A D and psi A Q, right. Therefore, when you substitute these incremental quantities, that is delta I Q, delta psi A D, delta I D, delta psi A Q, right, and these are the initial values. Okay. We can write down the expression for incremental change in air gap torque as K1 times delta delta plus K2 times delta psi A D. That is all the derivations which we have done right from beginning, right, were basically aimed to obtain an expression for change in air gap torque in terms of state variables, and we get an expression for incremental change in air gap torque, this delta T E, right, equal to K1 times delta delta plus K2 times delta psi A D. Okay. This is very important step. That is what we find here is that here that the delta T, there is change in air gap torque, depends upon the change in rotor angle, that is the power angle, and change in field flux linkages, that is delta psi F D. Okay. The model which I had derived earlier, where we assumed the field flux linkage is constant, right. The incremental change in torque, that is air gap torque, was simply equal to Ks into delta delta, while now here the incremental change depends upon the change in flux linkages in the field winding, field circuit, and delta delta. Okay. Therefore, now instead of representing the coefficient of delta delta as Ks, I am representing this as a K1. Okay. This is now going to be the difference in what we are writing. The expressions for these constants can now be written in the desired form, which can be computed from the knowledge of initial operating condition, synchronous machine parameters, and line parameters. Okay. These expressions have been derived because they are only the algebraic simplifications which we have to do. Okay. Just now let us look again at our mathematical model. This was the starting point for our further derivations. Okay. Now, this equation, right, has been linearized. In the previous case we have linearized it, where change in mechanical torque we have put as a delta T m, change in electrical torque as delta T e, and this is our damping torque term, right. And therefore, this equation, which is going to be a non-linear differential equation, the moment you linearize this, this becomes a linear differential equation, right. Now, we have now to linearize this equation, that is the field circuit equation. We have not done the linearization of the field circuit equation. This can be done very easily, because here we will consider the change in field voltage as delta EFD, okay, and change in field current as delta IFD. Okay. But this delta IFD, since this is not a state variable, is replaced by the incremental change in terms of the other state variables. Let us now examine the complete model of the system. These three equations represent the complete model of the system. First two equations represent the dynamics of the synchronous machine rotor or rotor dynamics. The third equation represents the dynamics of the synchronous machine field winding. These two equations were linearized earlier, and we obtained a simple state space simple model in the transfer function form. This third equation is now linearized, and when we linearize this equation, we will have the incremental change in field flux linkage, incremental change in field winding voltage, and the incremental change in field current. We have earlier obtained the expression for delta IFD in terms of state variables. Now, when we substitute the expression for delta IFD in this equation, the linearized equation can be now added to the first two state space equations, and the linearized equations appear in the form delta psi FD dot equal to A32 delta omega r, A3 plus A33 delta I am sorry, this last correction here. The delta psi FD dot appears as A32 delta delta plus A33 delta psi FD plus B32 delta EFD. Okay. This can be written in this form here as delta psi FD dot equal to A32 delta delta plus A33 delta psi FD plus B32 delta EFD. Now, we take the Laplace transform of this equation and obtain the transfer function model to represent this equation in the transfer function form. Once we take the Laplace transform, the equation can be written in terms of the Laplace transform variables, that is delta psi FD is equal to K3 divided by 1 plus P T3 into delta EFD minus K4 delta delta. Now, P is equal to S. Okay. Now, we will incorporate the transfer function relating, we will incorporate the transfer function relating the change in field winding flux linkages to change in rotor angle and field winding voltage. Earlier we had developed the transfer function model relating the variables considering the first two equations in the of the system. Now, to this model we will add the equation relating the field winding variables. Now, while deriving this model, we can do a small simplification, that is this portion of the model, can be simplified by using the simple block diagram simplification, and this portion can be represented by an equivalent model of the form 1 upon 2 times H S plus K D, where output of this will be delta omega r and input to this will be delta T m minus delta T e. With this simplification incorporated, the complete transfer function model incorporating the field circuit dynamics is shown here. This portion of the model is the one which was developed earlier. Now, since we have to incorporate the effect of field circuit dynamics, since delta T e is equal to K 1 delta delta plus K 2 delta psi f d, right. Therefore, at this summation point, we, to obtain the expression for delta T, we obtain a quantity equal to K 1 into delta delta, and to this we add a quantity corresponding to K 2 into delta delta and delta psi f d. Now, this sum is realized by using this summation block. Okay. Therefore, in this transfer function, delta T e is obtained by summing the two terms K 1 delta delta and K 2 delta psi f d. Okay. Then we have the transfer function to relate delta psi f d to delta E f d and delta delta. Now, this is shown in this portion of the block diagram, where input to this transfer function K 3 over 1 plus S times T 3 is delta E f d minus K 4 delta delta, right. Now, this K 4, K 3 and T 3 are again constants, and they depend upon the system operating condition and parameters. Now, therefore, this is the model which accounts for the synchronous machine field winding dynamics. Now, we will try to understand the effect of the including the synchronous machine field dynamics on damping and synchronizing torque coefficients. To examine this aspect, let us write down the delta T, that is the change in air gap torque produced due to the change in field flux linkages only, right. Therefore, delta T due to the change in field flux linkages can be related to the change in delta delta by this expression, the delta T divided by delta delta due to delta psi f d equal to minus K 3 K 2 K 3 K 4 divided by 1 plus s times T 3. Okay. Now, here we can examine the effect of frequency of oscillation of the rotor. In case the frequency of oscillation is 0, right, then we can substitute here in this equation or in this expression s equal to j omega equal to 0. Then delta T can be written as minus k 2 k 3 k 4 delta delta. That is, the change in air gap torque due to change in delta psi f d is expressed in the form given by this expression. Okay, this delta T is equal to minus k 2 k 3 k 4 delta delta. Further, we know that the change in the air gap torque due to change in delta delta, which operates directly, is written as delta T equal to k 1 delta delta, right. Therefore, we can say here the delta T E is written as k 1 minus k 2 k 3 k 4 into delta delta, when we consider the effect of change in field flux linkages also. Now, for any practical system, the constant k 2, k 3 and k 4 are positive, and we can see here that this term represents the net synchronizing torque coefficient, right, and when the field flux linkages were assumed to be constant, the synchronizing torque coefficient was equal to k 1, right. But the moment we account for the change in field flux linkages due to change in rotor angle delta, right, the net synchronizing torque coefficient decreases. It becomes k 1 minus k 2 k 3 k 4. Therefore, for steady state stability limit, the condition is k 1 equal to k 2 k 3 k 4. Okay. Now, let me conclude my presentation today here, that we have developed the small perturbation model of the machine infinite bus system, including the synchronous machine field winding dynamics. This model has 4 constants k 1, k 2, k 3, k 4, and we have also seen that when we account for the synchronous machine field dynamics, then the synchronizing torque coefficient under steady state operating condition decreases. That is, we can say that the demagnetizing effect has an adverse effect on the synchronizing torque coefficient. Thank you.